And so this is sort of the most concise way to define a first law of thermodynamics. The internal energy of an isolated system is constant. But what does it mean by system? How do you define a system? But you don't.
Yeah, isolated closed system.
Yeah, so is closed and isolated the same thing? That's interesting. That's a good question. Is it? Yeah, is closed and isolated the same? So we'll talk about that. What else? The reaction. Okay, that's typically, we don't really state it that well, but typically when we draw an equation on the board, a reaction on the board, that's our system. And so even though we may not have a hard boundary around it, like if a reaction generates gas, we may at a constant pressure let that gas go out into the atmosphere, but we'll draw an imaginary boundary around it. And we'll say, even though that gas mixes with nitrogen and oxygen in the atmosphere, conceptually, we will draw a boundary around it, and we'll talk about the work it took to push the atmosphere back. And so if you generate 1 mole of gas and it leaves the beaker, it's doing work by pushing back the atmosphere, even though we really can't see it, and we didn't put that in a piston and make it push a piston against 1 atmosphere. We could have done that if we wanted to, and if we had a friction-free piston. Okay, but we think of that system most of the time as the reaction. And so now let's isolated. Let's talk about isolated. We'll do that next. But here's another couple of ways to state that the first law of thermodynamics. You've heard energy is neither created nor destroyed, and I put the caveat on there, in a chemical reaction. Okay. And so in a nuclear reaction, we might have mass and energy converted one to another. And so you might say mass energy is conserved. So this quantity, mass energy, as one unit, either it's in the form of mass or in the form of energy, but that whole piece is conserved. And so there's the different types of systems. And so isolated and closed are different in one respect. A closed system can let energy in and out, but it's closed to mass leaving or coming in. An isolated system is no energy leaves and no mass leaves either, no matter leaves. And then an open system is open to lose or gain energy, and also lose and gain matter. So the simplest definition of an isolated system, as far as we can tell in our scientific endeavors, is that the universe is an isolated system. We really don't have any evidence for there anything being outside of our universe. Our universe is expanding, but the simplest understanding of our universe would be that it's an isolated system. And so it's neither, there's no place for mass to go outside of our universe. There's no place for energy to go that we know of. And so this is the thing that's, we're using terms like energy. I mean, this is the best definition that I can come up with and that I've ever read in terms of energy, but no one really knows, I mean, what is energy? Like the word is, what is it? What is its nature? What is its character? What makes energy energy? I mean, this is a strange definition if you look at it. It's not really telling you what energy is. Philosophical question, what is energy? I mean, it's a capacity to do work, but where does that capacity come from? It's a strange concept. A lot of these scientific things that we use every day, when you sit back and go, what's energy? I mean, what is it actually? It's a very bizarre question. We really don't have an answer for that. We can measure its relative amounts, and so we say if something has more energy than this, it has more capacity to do work than that. So we can relativize our energy. We try to find a reference point and set that to 0, and then we have things that are relative to that, higher energy or lower energy. But we don't really have a good answer for what is energy. And you probably never asked yourself that question, but because it kind of gets into the philosophical realm as to what actually is meant by that word energy. We know if we do work on a system, we're putting energy into that system. Okay, and then if the system does work, it's losing energy. So work is this way of transferring energy into and out of a system. And we can also gain or lose energy in the form of heat. And so work is the fundamental property in thermodynamics, really. The reason that is because it's measurable. Okay. We can kind of measure heat in terms of looking at the zeroth law and using temperature and thermal equilibrium. We can measure heat, but work is most easily measurable because you can see things like raising a weight, expanding a gas, driving electrical current. These are very measurable things, and so a lot of times we'll do heat by difference. Heat, since it is very hard to keep track of, we'll measure the work and we'll assume that whatever's missing is missing because of heat. Think about friction. We can measure how fast a car goes. We can measure how much gas we used. What's the difference? The difference is heat. But did we actually measure the heat flowing out of our engine, out of the air from our radiator, out of the heat from our tailpipe, out of the friction in our wheels, and so on? It's just so difficult to measure heat comprehensively that we'll measure work and take the difference and say that the rest is heat. And so the surroundings decide between whether it's heat or work. Disordered motion is heat, and ordered motion is work. So we really look to see if a system is sort of dissipating its energy to the environment, and the environment is just causing random, faster kinetic energy to the gases surrounding our system, then we say that we're losing that energy in the form of heat. Even if that gas around it is expanding a little bit, again, if you can't easily measure it, then you're just assuming that it's heat. But if all of that gas around it is going in a particular direction, if the expansion is ordered, then we would call that work. So notice just the difference in the two pictures. If it's surrounding our system, if it's disordered motion, we would call that heat. If it's ordered motion, then we would call that work. And so in action, if you've got the total energy is constant, and that's consisting of the change in energy of the system and the change in the energy of the surroundings. The whole system plus surroundings is the universe, and if the universe is isolated, then this total change in energy should be zero. So that's the shortest version of the idea of the first law of thermodynamics, is that if you've got the surroundings in the system, you've got everything. And so you've got an isolated system. It's either in the surroundings or in the system. And so if it flows out of the system, it must flow into the surroundings. And so we can move one to the other side, and they're equal in magnitude but opposite in sign. So if the system loses energy, then it's negative, and so then the surroundings would be positive, and so you put that negative sign in there to make the left equal the right. And so a lot of times for our chemical calculations, we'll ignore electrical changes and phase changes, and we'll just look at heat and expansion work. And so heat, in this case, is Q, and W is work. Unfortunately, Q is used for the partition function, but in this set of notes, Q is heat. Okay, so make sure that you don't get confused on that point. Now, if we have a change in internal energy with respect to temperature, that's the thermodynamic definition of heat capacity. So we talked about the equal partition theorem, and if you take the slope of 3/2 nRT with respect to temperature, obviously you get 3/2 nR. So our heat capacities for ideal gases, translation, rotation, and vibration. These are the things that molecules can do. We had 3/2 nRT was U, and then the heat capacity constant volume was the derivative of u with respect to t. So it's just 3/2 nr, number of moles. And then the rotation, if it was linear, you only had 2 degrees of freedom, so it was 2/2 nRT. Or 3/2 nRT for nonlinear. And so we had a heat capacity component due to rotation, and then vibration. Yeah, we have 2/2 nRT for every active vibration up to 3n minus 6. So this is really the most important piece for material science, and that is how many vibrations become active with temperature. So all of our properties, like those of you who are working with polymers, when you're dealing with glass transition temperatures, this is the thing that's causing those glass transition temperatures to be where they are. And so as you're raising the temperature, you're starting to activate certain vibrations, and then when they become active, now the polymer has different properties. Yes?
And so we consider active being specifically when it gets above the vibrational temperature?
Yeah, so let me draw a picture. This is what I'm thinking. So at low temperature, you have the vibrational potentials, right? And all your molecules are down in the ground state. And your temperature maybe is right here. And so you really don't have enough thermal energy to excite that vibration, so it's not active. And what we're talking about in terms of heat capacity and energy, we're not storing any energy in that vibrational mode because it's all at zero, if you will. Yeah, and plus the 0 point energy, but essentially it's static, it's not changing. But then as you start to raise the temperature, all of a sudden you've got a new bucket where you can put energy. Degeneracies change, right? Even if it's not degeneracy in the technical term, all of a sudden you have a new place to put energy. That changes your heat capacity dramatically. And so then it would be, again, 3 halves nR for active vibration. So when the temperature goes up, then you start to see some molecules appear here, and it changes the heat capacity. So the heat capacities are temperature dependent. And if you have a pretty large molecule, you've got a lot of really low frequency vibrations, and so some are active at low temperatures, and then you might saturate those really low ones, and then it's a little gap, and then all of a sudden you saturate some higher ones that really cause the mobility of the molecules to change with respect to each other. And that, again, in a polymer can cause a glass transition temperature. If you wonder what the glass transition temperature is in actuality, just think about a rubber hose and liquid nitrogen. Have you ever seen that demonstration? Put a regular Tygon tubing, put a rubber hose in liquid nitrogen, it goes below its glass transition temperature and becomes rigid. And you can smack it on a table and it breaks like glass. I mean, it is truly a great demonstration of a glass transition temperature. You smash it like a piece of glass and the shards go everywhere, and then when they warm back up, they're above their glass transition temperature, so they're in the plastic phase and they're flexible. So this elastic property will go away as you get below the glass transition temperature, and it turns into a hard amorphous glass, if you will, but it's rigid. So they're using the sort of the physical properties of rigidity to call it a glass. So it becomes rigid like a glass. Above that, it becomes plastic like a polymer. It's flexible. So that's sort of a bit of a review of the equipartition theorem as it relates to heat capacity. But these are the heat capacities at constant volume. Heat capacity at constant pressure is just this plus one more unit of R. So here's some materials for polyatomic gases. If you do these, various heat capacities, about 25 joules per mole Kelvin, 72 joules per mole Kelvin for room temperature water. Now we also, the heat capacity term is the per mole term. You might hear specific heat. And so whenever people put the specific term in there, they put that word specific. Yeah, it's per gram. So they're talking about masses then. Now the only other time I've seen that used where it's not per gram, it's just a ratio, is specific gravity. So specific gravity is the density of the substance divided by the density of water at that temperature. Well, the density of water essentially is 1, gram per mil, and so a lot of times the specific gravities and the density match because you're dividing by 1. But it's also at that temperature. So as you get to temperatures that are different than 25 C, then you'll start to get slightly different specific gravities. But those are finer points. And so since, again, work is 0 at constant volume, the change in temperature with heat input can be used to determine the heat capacity at constant volume. So you just look at the change in temperature and put in the heat capacity, and that's how you get the heat value. So we can, again, use the temperature changes to track heat. But it's just difficult to do that in all the ways a system can lose heat. Yes?
Is missing mass?
Where?
Q equals MC dot.
Number of moles, yeah. You can have number of moles in there. Yeah. If it's specific heat, you need the mass. And so then you have enthalpy. Again, our enthalpy values, this is the enthalpy is what takes place, change in heat at constant pressure. So that's why we use it so much in chemistry, because most of our systems are open to the atmosphere. And so this, at constant pressure, we're going to have essentially the enthalpy is that heat from the reaction. And so that's why we call it the heat of reaction. There is a difference between internal energy and enthalpy, which is essentially that PV work term. I think we were talking about that in one of the calculations that you were trying to do. And that it's just the number of moles of gas. And if the reaction doesn't generate or consume moles of gas, then H and U are the same. So you can get to internal energy through H if there's no moles of gas generated. If there are moles of gas generated, then you need to take those into account. So here's a review of some of the thermodynamic equations. We didn't derive all of these, but they are available in your texts. If any PChem text is going to have these derivations. The main thing I wanted to point out on this slide, though, was that relationship between CV and CP. So down in the bottom right, if you've got CV, you can get CP and vice versa. So they're just different by a unit of R. And the CP, the heat capacity at constant pressure, is just that the slope of enthalpy with respect to temperature, and the CV is the slope of energy or internal energy with respect to temperature. And so this is the second law of thermodynamics. No process is possible in which the sole result is the absorption of heat from a reservoir and its complete conversion into work. Now, this is what we would say prevents perpetual motion machines, because you can come up with something that is thermodynamically feasible, at least on paper, but whenever you try to make it actual, you always have entropy-driven processes like friction and other things. That just there's no practical way to do this. This would be isothermal expansion work, and if you look at this and you're doing the sort of the thermodynamic table for a cycle problem, during this leg, this reversible isothermal expansion, we have what looks like a violation of the second law of thermodynamics. We have the complete conversion of heat into work, or the complete conversion of work into heat. And so these are assumptions. They're never really actually reversible. They're never actually perfectly isothermal. And so these are sort of the upper limit of what we can do. And so if you did a Carnot cycle, which I kind of chose in this course not to repeat all of the Carnot cycle stuff because I wanted to get into the Hansen solubility parameters and some of the other like phase diagrams for mixtures and so on a little more deeply, and so something had to go. So for the Carnot cycle, you may need to review some of your notes for yourself. That we're not going to test on it, but that's something that has been omitted from this course. But that would be one of the legs of a Carnot cycle would be this reversible isothermal expansion, and then another leg would be the reversible isothermal compression. And those are very difficult in actuality to have happen because, again, this is saying that that process is actually not possible, that we're going to have some losses to heat. You're not going to be able to keep that exactly isothermal and exactly reversible. Now, this order to disorder is spontaneous, and we know that from our quantum mechanics two-level systems with and without degeneracy. So what do we mean by disorder? Essentially, at the quantum level, it just means statistically more options. Going from a two-level system without degeneracy to a two-level system with degeneracy, you've got 3 seats or 4 seats over here with degeneracy and only 2 over here without, and you're just going to populate all of those energy levels that you can, and so it's going to look like disorder. Disorder is kind of a slippery word. What does it mean, right? Because it's sort of the negation of order. Well, what is order? Order would be having everybody in one level. I mean, think about a pre-kindergarten class, right? All these little 4-year-olds running around. What would be order in that classroom? Everybody on the little reading mat, okay? Everybody on the carpet, and they're going to be all over the place, okay? Those are our molecules. So order would be everybody in the ground state, okay? It's reading time. We're going to have everybody in the ground state, calm. We're going to talk about this, but no. So quantum mechanically, disorder is measurable. It's the partition function. So entropy is tied to that partition function. If the partition function goes up, you have more disorder. Follow that? Yeah. And having the partition function be 1, that would be everybody in the ground state. And so what happens with temperature? With temperature, we have excitation. We have more molecules in different levels. We have a higher partition function. So entropy goes up with temperature. So hopefully, at least with this course and focusing on the quantum parts of thermodynamics, you now have a better understanding for what order and disorder mean. Order would be everybody populated, all the molecules in one energy level. Partition function of 1. And essentially, the entropy is the natural log of the partition function. And so the natural log of 1 is 0. And so if you had all of your molecules in the same energy level, the natural log of that would be 0, which would be your entropy. Your entropy term would be 0. If you raise the temperature and you get any molecules in any other energy levels, you've increased the disorder and your entropy has gone up. But that word disorder, I'm sure, has been something that you really haven't thought much about, just like you haven't thought much about energy, thinking deeply about these terms. Now, what's driving this spontaneity? Again, it's just losing those molecules to other populated levels. And so when a ball falls and hits the ground, its kinetic energy is turned into potential energy. It's squishing the ball. So it's like a spring. It squished the spring, but some of that is lost to heat in the vibrational modes in the polymers. Some of that's lost to heat in the vibrational modes in the desk or the floor or wherever that ball hit. And it's very difficult to get that energy back, to get those little pre-K and kindergarten kids back in the same energy levels they were in. And so you have, in engineering, 2 different kinds of terms. There's the loss modulus and the storage modulus. It's 2 different terms. And that loss modulus is what we're talking about. We're losing energy to those vibrational modes that are accessible, that are active. And the ones that aren't active are responsible for our storage modulus. We're storing energy in that's compressed ball, and we can get that energy back. So now it's not impossible for a ball will be sitting on the desk and then all of a sudden it just spontaneously hops straight up, but it's incredibly improbable. That would just be some random event where some wave in the table or whatever, just all of the molecules under that ball decided to go up at the same time and the ball jumps. But it's so improbable that we could say it never happens. Okay.
Would that be similar to microwaving a cup of water and it's undisturbed and all of a sudden you disturb it?
This would be water boiling without the microwave. The molecules could, a pocket of molecules could be above the boiling point, but all of the same ones in the same region is what's improbable, right? You've got molecules that are really hot in that flask and a lot that are really cold, and it's more probable that they're dispersed than that they're in the same location. And the same with the molecules in the top of a table. There are plenty of molecules in that table that have enough energy to bounce that ball back up. In fact, if you drop the ball on the table, you gave that energy to the table. But now those molecules are dispersed all throughout the table. It's not impossible for them to all come back and shoot that ball back up, but it's improbable, very improbable. Just think about a gas molecule, like a candle. If I light a candle here and it has a nice vanilla smell, that vanilla goes out through the room, and it's very non-spontaneous, very improbable for it to all collect back at the candle ever again. And the same with loss of energy in the tabletop. You could think of it as a gas, right? Those little hot molecules have now transferred their energy to other hot molecules, like transferred it away, and it's as if that gas has dispersed across the whole object. But it's not really a gas, it's photons of energy or phonons of energy, little pockets of energy, and those pockets of energy also spontaneously spread out. And it's just improbable that they're going to come back and create a hot spot. Okay. Statistically, again, the statistical treatment, you can't say it's impossible, but it's so improbable. Yeah, like probably 10 to the minus 50 or something like that. And so when stuff gets that small in probability, there's really no difference than saying it's zero. But if you were to tell me, is this possible? I'll say, well, yeah, it's possible, but it's not improbable, but it's improbable. It's not reasonable to believe. I don't see things just hopping off the ground. If it does, I look to see what the cause was. I don't think, statistically that could happen. Right? So, what's that? We use those improbabilities to kind of figure out when somebody did something, right? If somebody moved my hat, it's possible the hat just bounced someplace. But it's so improbable that it's much more likely that I would say somebody moved it. That there was an agent involved, because the probabilities are so low that we would go to agency. Yeah, somebody, yeah. It's more likely that somebody close to the hat moved it than somebody far away.
If you're not looking at it, it could be Schrodinger's hat.
It could be Schrodinger's hat, you're right. And so that's what I'm talking about, the difference between probability and possibility, yes. So we get into these definitions of entropy. This isolated system that we're talking about, the universe, it's increasing over time in the cause of spontaneous change, and it's still very low. That's a big deal that our universe still has burning stars and planets and ice comets and so on. And so if we had this reversible isothermal expansion of an ideal gas where we have the Q equals minus W, and delta S is that Q over T. We can take that equation for isothermal reversible expansion of a gas, put that over T so the T's cancel, and so we can calculate the entropy change in that spontaneous expansion. And we can also reduce the entropy by compressing the gas. So if you cram a gas into a small space, if you make all the kindergartners sit in the corner, right, you're lowering the entropy, and you can do that, okay? But spontaneously, it's going to want to fight you. It's going to go the other way. And so you can look at the natural log there and say if the volume final is greater than the volume initial, then that ratio is greater than 1. And so then the natural log is positive. But if I compress my little kindergartners and get them in the corner, the V final is less than V initial. And so I have a ratio that's less than 1, so the natural log is negative. And so that would be a decrease in entropy. Now we get to the third law of thermodynamics. Just check time. And so at T equals 0, all the excited state energy has been sucked out of the system. And so think of the quantum mechanical example. All of the molecules go to their ground states. We set those ground states. Essentially we count those as, that partition function is 1 because we set that energy to 0. And so we have an entropy of 0. So S goes towards 0 as temperature goes towards 0. And so the entropy of a perfect crystalline atomic substance is 0 at T equals 0. So that's sort of a definitional statement for entropy. And now that we have that reference point, we can make tables. So that's where our entropy tables come from. We can talk about entropy of phase transitions. It's that change in temperature or heat with respect to change in heat with respect to temperature. We get the entropy change for that phase transition. So let's look at some of those phase transitions. So you're kind of going along over here on the chart. If this is an atomic substance at T equals 0, it has an entropy of 0. And the entropy grows as you warm it up. And then you hit that phase transition. As you're going from solid to liquid, you're giving those molecules a much larger box to move around in. So if you think of a particle in a box, as you increase the box, the energy levels get closer together because L, the box length, is in the denominator. So you put something in a larger container and give it more freedom, its entropy goes up because it can populate many more translational energy levels. Okay. And so this solid now is a liquid, and even though it may be in a large container, it may not really have the full container to move around in toward sort of on a quantum scale, right? Because it's still got neighbors. It's in a cage of other molecules. So its box is increased, but not by much. The real increase is when you vaporize that liquid and become a gas. Now that gas molecule can go from one wall all the way to the other, and the number of translational energy levels is on the order of 10 to the 40 populated at room temperature. So your partition function is on the order of 10 to the 40 for a translational partition function for a monatomic gas. And so then these slopes in between just show that the entropy increases with temperature. So we have this long equation which has the heat capacities and the delta H of fusion and the delta H of vaporization. So we can start at 0 and calculate the entropy for any substance all the way up as high as you want to go. Here is some experimental data for oxygen. The entropy chart's on the left. The heat capacity chart is on the right. And it's kind of nice. We see those different heat capacities for translation, rotation, vibration, etc. So we have 3/2 R for translation, 5/2 because it's a linear molecule for rotation, and then for vibrations, let's see, 3/2 R translation, 5/2 R vibration. We've got another R for the vibration. So for oxygen, we see that full equipartition heat capacity over there on the right when it's a gas. What's interesting though is when it's a liquid, look how much higher the heat capacity is. So what's going on for liquid oxygen? Why is the heat capacity so high? Because oxygen can do 3 things. It can translate, rotate, and vibrate. What else? Where is it storing that energy? And this will be the last thing, because we've got like 1 minute.
Intermolecular interactions?
Yeah, so what is, think about a liquid, the nature of a liquid. And so now what used to be translations is really low frequency vibrations. They're called acoustic modes. Why would they be called acoustic modes? So you have modes of vibration. That's the O stretch. That's it. That's all you've got for O2. So that's a vibrational mode. But now we have in the liquid oxygen acoustic modes. Think about the speed of sound through that liquid. What's going on with the speed of sound? You've got molecules banging into molecules, and then they come back. So there's an oscillatory nature to materials, and you can store energy there. And so you can actually, in a liquid, have a higher heat capacity than what you get for a gas, and also for a solid, you see.
Does the hydrogen bonding and oxygen help, or?
This is pure oxygen, so yeah, there's nothing there.
Pure oxygen?
Yeah. And so this is just acoustic modes in the liquid. So you might have two oxygen molecules vibrating, or just, against each other. You may have a cluster of oxygens. You may have different angles of striking. You can have librations. So some of the rotations turn into vibrations where they don't rotate all the way around. They bump into each other like that. And so you have these resonances in the liquid state and in the solid state that are between clumps of molecules, and those are called acoustic modes. And you can store energy there too, quite a bit of energy. That's where some of the ultrasonics come from. We get these cavitations and so on. Yes?
So the solid 1, 2, 3 regards to like the different things.
Yeah, next when we get to phase diagrams, we'll talk about different solid phases. And so different configurations, maybe T, maybe triangular, not triangular, but tetrahedral. And so you can have solid of structure 1, structure 2, structure 3. And so there's 3 solid structures in oxygen. There's like 7 or 8, or maybe even I think up to 13 now in water. It's ridiculous. I don't know how you can come up with 13 structures of water. But it's really very crazy. So that's sort of a review of the 3 laws of thermodynamics plus the 0th law last time. Next time, remember 2 slides on your project.